All right. Using standard reduction potentials, I'm going to give you these values on the test whenever they're needed. What is K for the reaction listed below? Okay, so the first thing that we need to do for this is we need to figure out what are our standard reduction potentials for these reactions. What I see is that Fe 2 plus 2 electrons yields Fe, and you get an E naught of negative 0.45. Okay, now my other reaction is nickel, Ni2 plus 2 electrons. Ni2 plus 2 electrons yields Ni, and we have a negative 0.26. Okay, so that's useful information. Now what we need to do is we need to figure out our E naught cell for this. Well, what takes place at our cathode? Well, what takes place at our cathode is our reduction. Which of these species is getting reduced? Well, iron is going from 0 to iron 2 plus. So this is getting oxidized. Therefore, our nickel going from 2 plus to nothing is getting reduced. Okay, so what we want to do is we want to say, what is the value that's getting reduced? And what we see is that this negative 0.26 minus our other value, what's taking place at our anode, our negative 0.45. That's what we've got going on there. So we have 0.26 negative minus, and then in parentheses, 0.45 negative, close parentheses, and we get an E naught cell of 0.19. Okay, now what we want to figure out for this is we want to look at our relationships between E naught cell and any sort of equilibrium constant there. And so what we can do is we can look at our relationship between this reaction or this equation and our log of K. We can go ahead and look at our equations and say, well, we know that delta G naught equals negative NFE naught. We also know that delta G naught equals negative RT ln K. Okay. Now, as a result of this, we can say negative NFE naught is equal to negative RT ln K. We can use that to say, well, NFE naught equals RT ln K. What we want to solve for is this K. So I'm going to put that by itself. I'm going to say NFE naught divided by RT is equal to ln K. And it's at this point that I want to start worrying about plugging any values in. Well, this is happening at 298 Kelvin. And I know that because temperature is not mentioned. What I'm going to do is I'm going to come over here using this equation, and I'm going to say N, the number of electrons that are being transferred. That is 2. Times F, which is 96,485 times E naught, which I just solved for, 0.19 divided by my RT. What is my RT? My RT is going to be 8.314 joules per mole Kelvin times my temperature, which is 298 Kelvin, and I'm going to end up with, well, a number that relates there. So what I'm going to end up with is 2 times 96485 times 0.19 equals, I always like to write my numbers out, 3664.3 divided by 8.314 times 298 equals 2477.572. Okay, so 3664.3 divided by 2477.572 equals 14.798. So I'm going to call that 14.8. And my units that are left behind are just going to be, let's see, coulombs, I believe it would be. Or no, sorry, yeah, this is equal to ln(k). Now what I want to do is I want to take both of these values and raise them to the e power. And I will do that with my calculator. Now, when I raise that 14.8, the way that I do it on my calculator is I punch in 14.8, and then I've got this function that is shift, and then right above my natural log is what undoes my natural log. So I hit that, and I get that number right there. And that is my k value, which is k is equal to 2676445.055. This is an equilibrium constant that totally favors my products, but that's my k value. I think a better way of writing that would be equals, let's call that 2.68 times 10 to the 1, 2, 3, 4, 5, 6 to the 6th. There you go. I hope that was helpful, and I hope that illustrated some topics along the way.